we have two balls, ball 1 and ball 2, and we know that ball 2 has twice the mass of ball 1. And then we're given that the ball 1 has a mass of 60 grams, so that must mean ball 2 is 60 times 2, so 120 grams. Okay, it starts 30 centimeters below the peg. Calculate the tension in the string and the time taken for ball 1 to reach the peg. Okay, so starting off, I'm going to model ball 1. We know that ball 1 is moving upwards, so I'm going to take upwards as positive. What forces do we have acting on it, upwards or downwards? So just in the vertical direction, basically. We have T, which is going straight up, so that's positive. And then we have its weight, which is going down, so we're going to take that away. How do we work out weight? Well, we would use F equals MA, where mass, in the case of ball 1, is 60 grams, but we need SI units, so 60 grams equals 0.06 kilograms. And acceleration is G in the case of its weight. Okay, so this will be 0.06 times by 9.8. And if you work that out, that is equal to T minus, put that bit in your calculator, 0.588. Okay, so that doesn't mean a whole lot at the moment. One thing that we can do extra is the fact that this is going to be a force, isn't it? We're working out a resultant force, and then we can also use F equals ma for a resultant force. We know the mass, we don't know the acceleration, so we can write T minus 0.588 is equal to 0.06 times our acceleration. Okay, so doing a very similar thing for ball 2, we know that W2 is going to be greater than T in this case because we know the ball moves downwards. So we're going to have W2, which is going to be 0.12 times gravity again. And then take away the tension because we know it's moving down. This will be equal to 1.176 minus T. So you can see a very similar equation here. And again, using F equals ma, we can set that equal to 0.12 because that's the mass. 120 grams is 0.12 kilograms times acceleration. Okay, both of those A's are equal. So you can see that this one is double that one. Okay, so using that fact, we can solve for T because if we double this and set it equal to this, we have a linear equation. So we'll have two lots of T minus 0.588 equals 1.176 minus T. Okay, so now I would expand these brackets and then we have a linear equation to solve. So we'll have, expanding that bracket, we'll have 2T minus 1.176. Okay, so solving this bit here, what will we get? Well, we can solve it and get T equals 0.784 newtons. So all you would do there, I would add that T on, you'd get 3T here, and then add this on to here, and then divide by 3, and we end up with this. Okay, so now we can figure out what acceleration each particle has. And of course, because they're connected by a string, we can model it as one. They're both going to have the same acceleration, but they are going to be in opposite directions. One's moving down, one's moving up. Okay, so figuring out the acceleration for ball 2, so A2 for ball 2 is going to be 1.176, take away our tension that we just worked out to be 0.784, over its mass, because basically I'm rearranging this equation here. What does that give us? Well, that gives us 3.27, and then it's an acceleration, so meters per second squared, that's to 2 dp. So we have the acceleration of ball 2, that's 3.27 meters per second squared. That's also going to be the acceleration for ball 1, because of course they have the exact same acceleration, just in opposite directions. So using SUVAT, we can figure out how long it takes for it to reach the peg. So we'll have S, well, that's got to go 0.3 meters, because it says it starts 30 centimeters below the peg. U is going to be 0, okay, because it's starting statically, so starting from sort of a dead stop. V, we don't know and we don't care. A, we know is 3.27 meters per second squared, and of course that's in meters. T, we don't know, but that is what we're trying to find. Okay, so subbing this in to s equals ut plus a half at squared, so just one of the Suvat equations, we're going to have 0.3 equals ut, we'll use 0, so that whole thing's just 0, plus half times acceleration, which was 3.27, times t squared. Okay, now we can solve this problem, and you'll actually get two solutions because, of course, it's t squared, so when you square root it, you get a positive solution and a negative solution. You can't have a negative time, so initially you would get this, t equals plus or minus 0.43 seconds, but t cannot equal minus 0.43 because you can't have a negative time, so then t equals 0.43 seconds. That's how long it takes for ball 1 to reach the peg. So imagine a system of two weights attached by a thin piece of taut rope, both of mass 4 kilograms. Weight A is rested on a rough table with a coefficient of 0.2, so it means a coefficient of friction, and weight B is suspended below a smooth pulley. What is the acceleration of both weights? What is the tension in the rope? Well, what is the acceleration of both weights? They're going to be exactly the same. So if we can work out one, we also have the solution for the other. And then what is the tension in the rope? Well, that's acting here, but it's also acting here. Okay, so we've got a few forces that we can model here. So they're already labelled A and B. So for B, we only have vertical forces, don't we? We have its weight pulling down and we have the tension pulling it up. Okay, we know that the weight is going to move down and A will move this way. Okay, we know that because, of course, it's not going to move up, but also notice that says F there. So that's the friction, and it moves in the opposite direction. The friction acts in the opposite direction of the motion. Okay. So what can we do now then? We can take the vertical direction for B. So the resultant forces are going to be its weight minus the tension. So it's going to be mg minus t. In this case, do we know the weight? Yep, the mass. They're both 4 kilograms, so it's going to be 4g minus t. So therefore, it's going to be 39.2 minus t. And using F equals ma, we know that this is a resultant force that we just found. We know its mass, so we can write this as 4a. Okay. So what else can we do? We can figure out the vertical direction. So that was for B. We can figure out the vertical direction for A. Okay, there's only two forces acting in the vertical direction on A. You've got its weight and you've got the normal reaction. So we then therefore know that one minus the other is going to be 0, isn't it? Because it's not accelerating in either direction. Okay, so we can say that R equals mg in the case of A. And we know that m is 4, we know that g is 9.8, so R equals 4 times 9.8, which is 39.2 newtons. Okay, so what else can we solve for? Well, we can solve horizontally for A. What's the resultant force going to be horizontally? You're going to have the tension, because we know it's moving left, so it's the tension, take away whatever friction does. Well, friction is F equals, that's a terrible mu, sorry, F equals mu R, okay? We know mu is the coefficient of friction, which is 0.2, and we know R is 39.2. So it's going to be T minus F, which we know is T minus 0.2 times 39.2, okay? So then that is T minus 7.84. And again, using F equals ma, similar to what we did for the vertical direction of B, we can say that that's equal to 4a as well. Okay, can you spot what we're going to do next? We've got two equations, both in T and in A. So we have simultaneous equations, and nicely, they're both equal to 4a, so we can just set them equal to each other. We've got T minus 7.84, that comes from this one, is equal to 39.2 minus t. Okay, so we've got a linear equation that we need to solve. How can we solve it? Well, you would add the t and then add this on, and you would get 2t equals something. and then we can solve for t. So that gives us t equals 23.52 newtons. Okay, so we found t, which is the tension in the rope, so that's that bit done. What is the acceleration of both weights? Well, we previously said that they're the same, so we can just use one of the equations. This one's probably the easier one to use. Sub t in, and then divide by 4. So we'd do 23.52 minus 7.84, and I said divide by 4 because we've got 4a, we only want a. So if you do that, you would get 3.92, and of course this is an acceleration, so meters per second squared. As I said previously, because these are connected particles, if one has a certain acceleration, the other has the exact same acceleration, and in this case it's sort of in the same direction. As this is moving this way, it just follows the path of the rope. Okay, so they're both moving that sort of direction. So we've got another system of two weights attached by a thin piece of taut rope. Weight A has a mass of 9 kilograms and is on an inclined plane at an angle of 45 degrees. So we can see that that is 45. Then we have a coefficient of 0.1, which is a coefficient of friction. Okay, so we know that mu is 0.1. And a weight B of mass 3 kilograms suspended below a smooth pulley. Does weight B rise or fall? What is the rate of acceleration of both weights? What is the tension in the rope? Okay, so there's a couple more things we can put on there. We know we have the weight, which is going straight down. That's going to be 9g for A because it's a mass of 9 kilograms. So mass times acceleration, acceleration in this case being gravity or g. And then the weight for B is going to be 3g for the same reasoning, but this one has mass of 3 kilograms. Okay, so there's a few things that we consider. The issue we've got first is if we want to work with A, we need to work parallel and perpendicular to the plane. But you can see this force is not acting parallel or perpendicular. Okay, so what I would therefore do is draw a bit of a triangle. It's right angled here, and then we know this side is perpendicular to the plane and this side is parallel. So how would you work those out? Well, this would be an angle of 45. So then the bit going perpendicular to the plane is going to be the weight times cos 45. So it's going to be 9g cos 45. Okay. And if you stick this in your calculator, we're going to keep it reasonably nice so that we don't have any rounding errors. It's going to be 88.2 over root 2. Okay, then we're going to work parallel to the plane. Okay, and we need to form some sort of equation. What do we have going parallel? Well, we have t going this way, and we have some component of the weight going this way. So is it going to act up or down? For now, we don't really know, but we do know there is some friction because it says a coefficient of 0.1. Okay, so I'm going to imagine that it's acting down and just take mg sine 45. In this case, we know what mg is. It's 9g. So it's going to be 9g sine 45. Sine, because this case we're working out the opposite here of the triangle that we drew. Minus the tension, because that's going up the plane. And then minus the friction, because we're imagining it's going down. Okay. And then that can be simplified a little bit to... well, not simplified, I suppose. It would be 9g sine 45 minus t minus friction that we know has a coefficient of 0.1, and the normal reaction will be exactly the same as this. So 0.1 times that. So 0.1 times 88.2 over root 2. The reason it's exactly the same is because those are the only forces acting perpendicular to the plane, and we know that it's not coming off the plane or going through the plane, so they must be equal. Okay, so what can we do from here? We can figure out quite a big chunk of this. We know what 9g sine 45 works out, so you can just stick that in a calculator. You can stick the last part in a calculator. So we end up with 88.2 over root 2 minus t minus 8.82 over root 2. Again, we could simplify this a little bit because obviously these are both over root 2, and that will equal 9a because of F equals ma. This is a resultant force that we're working out. So we know the mass, we just don't know a. The mass was 9 kilograms, so 9a. Okay, so we're going to imagine now that weight B is moving upwards. What forces are acting on it? Well, you've got T and you've got its weight coming down. So T is the tension. So it's just going to be T minus its weight, which we said was 3G. And again, this is a resultant force, so it's going to be 3A. Okay? So we can actually use the two equations. So we've got these two equations here. They're both in T and in A, so we could solve for either of those. Okay? So what I would do here is I would times this equation by 3 and then set it equal to this. And solving will give us T equals 36.08 newtons, and I'm just giving that to 2dp. It is slightly longer, but we'll use 2 decimal places so that it's pretty accurate, but we don't have to write a stupid amount of numbers. So then you could stick this straight back into here for T and figure out what A is, and in that case you'll get A equals 2.23 meters per second squared,